Walking is one of the most fundamental things we do as humans, but people who suffer from spinal cord injury, stroke, MS, traumatic brain injury, and other impairments often have to relearn how to walk as adults. Robots are increasingly being used in rehabilitation treatment, with the robot teaching the patient how to walk again. Researchers from the Spaulding Rehabilitation Hospital and the Wyss Institute at Harvard University are exploring how people modify their gait patterns in response to interacting with these robots. The researchers are interested in understanding the neural mechanisms that people use to respond to the forces that the robots exert. In their experiments, a robotic system designed for treadmill-based gait retraining was used to apply forces that disrupted a subject's step length, either by increasing it or decreasing it. The team investigated how the neural control of muscles changed during the two experiments by recording electrical signals from the subject's muscles. The analysis of these electrical signals, called electromyographic signals, allow researchers to understand how the brain controls gait movements. By performing these analyses, researchers found that the nervous system responded to the two perturbations using different combinations of feed-forward and feed-back commands to the muscles. Feed-forward commands are driven primarily by the cerebellum and result in slow change in the descending cortical drive. Feedback commands originate at the spinal level and rapidly affect neural circuits referred to as central pattern generators. Specifically, researchers found that the response to the perturbation causing an increase in step length was mainly driven by feed-forward control originating at the cerebellar level, whereas the response to the perturbation causing a decrease in step length was driven by both feed-forward commands originated at the cerebellar level and feedback control originated at the spinal level. Spinal control is marked by fast changes in the muscular activations, aiming at responding to sudden threats such as slippages or stumbles. Both types of command project onto the same spinal interneuronal networks that encode locomotor muscle synergies. This observation has important implications for rehabilitation robotic use and how therapists design treatments with motor impairment.